Welcome to This Explainer. Today we're unpacking a really fascinating story in the history of software engineering. We're looking at exactly how Bjarne Stroustrup built C++, which is, still one of the most widely used programming languages in the world. But here's the secret about C++. He didn't build it out of pristine academic theory, not at all. He built it out of intense, unavoidable engineering constraints.
You've probably heard this famous quote from Stroustrup himself. It's got that classic dry wit, right? But it brilliantly illustrates the immense power and, let's be honest, the potential danger of this foundational language. C++ absolutely gives you the tools to build incredibly complex and highly efficient systems, but it demands that you know exactly what you're doing.
So, here is our roadmap for today. We're going to logically walk through the historical anecdotes of the language's creation, look under the hood at its deep architecture, and then finish up with Stroustrup's modern philosophy on where software's heading next. Section 1. The origin problem. The tension at Cambridge.
Okay, so the core problem Stroustrup faced back when he was a PhD student at Cambridge was a classic software dilemma. He was trying to build a distributed system simulator, and he was stuck between two extremes. On one hand, you had Simula. Now, Simula had excellent classes and really high-level conceptual organization, which was perfect for simulation, but it was just way too slow and resource-heavy for his environment. On the other hand, you had languages like BCPL and C. Those were blazingly fast and close to the hardware, but they completely lacked the organizational structure you need for a complex system. He basically needed a bridge between these two worlds.
And the crucial takeaway here is that his solution wasn't to just invent a whole new programming paradigm from scratch. It was a purely pragmatic synthesis. He started with what he literally called C with classes. Why? Well, because he needed a single language that could be used to write low-level device drivers and memory managers, but could simultaneously support high-level, multi-person network protocols to build a distributed Unix system. He needed the absolute best of both worlds.
Section 2. The Bell Labs Incubator, Freedom and Practicality.
Fast forward to 1979. Stroustrup joins Bell Labs, which was an incredibly fertile ground for innovation at the time. And their research mandate was almost shockingly simple. It was literally just do something interesting. They hired strong people, gave them room to breathe, and just let them work. This meant C++ grew organically. It evolved by being used by actual colleagues to solve real-world problems, rather than being, designed by some corporate product committee in a vacuum.
But don't get me wrong, it wasn't just unstructured playtime. Bell Labs had a pretty brilliant cultural rule: the annual one-page readable report. This forced strict, intense focus. Think about it. If you couldn't explain your entire year's research in a concise, readable one-page summary, your work simply wasn't focused enough. So C++ was born right out of this intense, practical engineering environment driven by immediate problems, rather than a clean theoretical agenda.
Section 3. Pragmatic design, trade-offs, and the blueprint.
Now let's talk about the absolute core of C++'s performance philosophy, the zero overhead principle. It dictates that you shouldn't pay any performance penalty for language features you aren't actively using. And when you do use an abstraction, it should run just as efficiently as if you had painstakingly written the low-level code by hand yourself.
But Stroustrup actually pushes this even further, often giving the advice, don't be clever. Now, what he means by this is that writing clear, straightforward, modern C++ can actually achieve what he calls negative overhead. Wait, negative overhead? How is that possible? Well, it's because a clean abstraction, like a standard container, gives the modern compiler way more structured information to analyze and optimize than a tangled, handwritten, supposedly clever C-pointer implementation ever would.
Strategically, basing this whole thing on C was a brilliant bet. Bell Labs already had C linkers and optimizers everywhere, so adoption was super rapid. But of course, there was a cost. C++ inherited C's unsafe implicit conversions, meaning data types could silently change and cause totally unexpected behavior. Also, prioritizing static typing wasn't just a stylistic choice, it was life or death. Stroustrup was designing for early 1980s low-memory machines that absolutely couldn't afford runtime checks, and for safety-critical telecom systems where there's no developer sitting at the terminal to handle a crash if a type error happens at runtime. The compiler had to catch it early.
Section 4. Standardization and safety, from corporate pressure to modern profiles. As C++ grew massive, major corporations realized they needed a stable, vendor-neutral specification before they can depend on it at scale. Looking back at the timeline, it was really this corporate pressure that led to the ANSI committee forming in 1989, which was based off the annotated C++ reference manual. That built up to the first ISO standard in 1998, all the way to the C++23 standard we have today. Formalizing the language was a corporate necessity.
So when we talk about safety in modern C++, we're not talking about a single magic feature. It is very much a layered approach. We're talking about things like standard span, introduced in C++20, rigorous static analysis, and RAII, which essentially ties resource life cycles directly to object lifetimes so you just don't leak memory. And this illustrates Stroustrup's recent focus, profiles, which he detailed in a draft paper aiming for 2026. Profiles are basically enforceable subsets of C++ that guarantee type and resource safety without throwing away the language's core compatibility and performance. It's all about making safety incremental and adoptable.
Section 5. The Vasa syndrome, sinking the ship with features.
I love this part. This is one of Stroustrup's absolute favorite historical metaphors when he addresses modern criticisms of software bloat. Okay, picture this. It's 1628, and the Swedish king, Gustavus Adolphus, orders a massive, heavily armed warship called the Vasa. But because it was incredibly top-heavy with 2 huge gun decks and possessed a fatally unstable design, it catastrophically sank on its very first voyage, just right into the harbor.
So, what are the direct software engineering lessons we take from this historical disaster? Number 1, do not add features on a weak foundation. Number 2, never compromise testing when evidence shows instability. And number 3, professionals must resist management pressure when a design is demonstrably unsafe. For C++, Stroustrup uses this as a direct warning to the Standards Committee. Simply piling on new features is so much easier than preserving the structural coherence of the language itself.
Section 6. Hindsight and Future, AI, Regrets, and Lessons Learned.
Looking forward, Stroustrup has a very specific skepticism regarding modern AI code generation. He totally agrees it has strengths, like churning out routine code and writing documentation, but the risks? They're massive, especially in safety-critical systems. The burden of validating all that AI output falls entirely on senior engineers, and honestly, even more concerning is the pipeline risk. Think about it. If we automate away all the junior programming work, how does the industry ever train the next generation of experienced senior engineers?
Looking back, Stroustrup is remarkably candid about his regrets with C++. He really wishes he had fought harder against those unsafe narrowing conversions inherited from C. He regrets that early C++ had weak generic facilities, and today he's highly critical of how large, unwieldy voting bodies handle standardization. But really, these regrets just show us something fascinating. The exact constraints that made C++ successful and adoptable in the early days are the exact same things that cause its hardest ongoing problems today.
And that leads us to this incredibly powerful piece of advice from Stroustrup regarding language design and software architecture in general. Always improve the foundation. Don't just hack on features, make the base stronger.
If there is one single thing you take away from this explainer for your own career, let it be this. C++ is a remarkably pragmatic tool. Its history teaches us to define the problem first, heavily respect our constraints, preserve performance where it actually matters, and above all, empower programmers to express their true intent without losing control over the machine.
Which leaves us with this final thought as you look at your own software designs today. Really ask yourself, are we designing tools that actually help us express intent and solve real problems? Or are we just piling on features and building another top-heavy Vasa? Thanks for joining me, and keep learning.